Okay, our point 7 continued. We're going to work with the radicals some more towards the last of this lesson on example 9. We can use the FOIL method. We can add, subtract, multiply, and divide radicals. So we're kind of working through all the different operations with radicals. So in the earlier lecture, we talked about how you can simplify radicals. If you just have one radical, you should try to bring out any of its perfect parts and simplify it down. And now, so then if you do have common radicals, you can add and subtract. For example, square root of 2 plus, let's say, 2 square root of 2 plus 3 square root of 2 would be 5 square root of 2. So common radicals can be combined. If you had 6 cube root of x plus 7 cube root of x, you would have 13 cube root of x. So like radicals can be added or subtracted. So that's that part of it, the rule for add and subtract, just like bases. Now we're going to move to multiply. So we're actually in the FOIL method here. We've got 2 radicals times 2 radicals, which would be 2 things times 2 things is foiling. So we have to FOIL this. So we'll do the first times the first, square root of 7 times square root of 7. We can multiply what's under there. It's square root of 49. That's perfect, just regular 7. You could also reason that out, that a square root times itself would be like squaring a square root. So it kind of cancels out the square and square root cancel each other out, bringing out the 7. The outer, 7 times 10 is going to stay in the radical, 70, square root of 70 there, which won't reduce. Inner times inner, notice I have a negative times a positive, so it's negative, and again, 10 times 7. If they're the same root, if you're timesing a square root times a square root, they have to be like rooted, then you can multiply what's under them. So that's how I'm able to do 10 times 7 is 70. Then last times last for the L, a negative times a positive is negative. 10 times 10 is 100, square root of 100 is 10. That's one thought. Or a radical times the same radical is like squaring a square root, and that just brings out the 10. So then combine any like terms. These are exact opposites. They cancel. 7 minus 10 is negative 3. Final answer for all of that. I'm surprised it reduced nicely to just negative 3. Actually, what we're going to learn as we go through this section is this is called the sum and difference of 2 terms. And when you multiply by that, it's always going to cancel out the radical for you. You're always going to be able to get to a rational number, just a nice number with that method. We're going to see that in the later problems. Okay, before we do, let's use the FOIL method again here on example B. So this one won't reduce down quite as nicely, but it does reduce some. So FOIL again, because it's a binomial times a binomial. The first times the first, because they're both square roots, we can take the 2 times 8 and get 16, which will reduce to just a 4. The outer times outer, so this one's in a radical and this one's not, so we write that as 5 radical 2. We just put the negative 5 in front of the radical 2. And then the inner, sort of the same strategy, 3 radical 8. And then the last times last, just regular rational numbers, 3 times minus 5, negative 15. All right, we can reduce this a bit. The 4 and the minus 15 maybe is the more obvious part, is negative 11. But what about these radicals? This square root of 8 will actually reduce, and we're always required to reduce when possible. So 8, while it's not perfect, it does contain a factor of 4. 4 times 2 is 8. The square root of 4 is perfect, can come out of the radical as a 2, multiplying onto the 3, giving us a 6 radical 2. So this reduces to 6 radical 2. And then it is a like radical. Minus 5 radical 2 and 6 radical 2 will give us a positive 1 radical 2. And then that would be our final, most reduced form of that. All right, so we can multiply with radicals if they're like rooted, and then reduce if possible. The last part of this section is all about dividing with radicals. So what if you have the division of a radical? Well, you're never supposed to leave a radical in the denominator of a fraction. So we always are required to rationalize. You'll sometimes call it rationalizing the denominator. Rational means there's no longer a radical there. It's a number that could be expressed as a fraction. And so when it's in the radical, a non-perfect radical is actually irrational. If you type square root of 3 equals on your calculator, you're going to get a long answer. It actually never terminates. It never repeats. It's just kind of cut off of the 10-digit calculator, but it doesn't really stop. It's sort of like pi. Pi is like that. It's a maybe popular irrational number, one of those that keeps going on and on and on. So irrational numbers go on and on and on. They never stop. They never repeat. So there's not a good way to cut those off without some rounding, and then there's round off errors. So it's not an exact math. So we want to try to clean that up and get rid of the radical. Well, the way we do that is we times it by something that makes it perfect. A lot of times it's just timesing it by itself. In this case it is. Radical 3 times radical 3 would be just a regular 3. It'd bring the 3 out, and it'd be rational. Well, we can't just go around changing our fraction just because we feel like it in the denominator. We have to keep the balance in algebra. So what you do at the bottom, you do to the top. So if I times the denominator by radical 3, I have to times the numerator by radical 3. Then 4 radical 3 is just 4 radical 3. And then that is how we more appropriately leave our reduced answer. No, it doesn't look much reduced, but that is the preferred over that. Let's try it again. Let me just make one similar to that. Let's say we had 2 over radical 5. And you might want to pause and practice this. But I would times it by radical 5 to make that a matching set, and times the top also by radical 5. You get 2 radical 5 for the top. And then this will be radical 25, or just 5, or also the reasoning, a radical times itself just brings the radical out. It squares the square root. What if I had 2 over radical, let's say 6? I could times that by another radical 6, top and bottom, which makes 2 radical 6 over regular 6. This one will reduce. The 2 and the 6 can be reduced to 1/3. So you should always reduce if possible. So, all right. So what if we're doing a higher power instead of just a square root? Say we're doing 2 over cube root of 2. Then we need to make it a perfect cube. So just timesing it by 1 more of those wouldn't be enough. We need 2 more 2's. You know, you need it to be divisible by 3. So we got 2 to the first. We're going to need 2 more 2's to make it 2 to the third to work. So you need to make these into something that will be perfect. And then whatever you decide, do it to top and bottom equally. So the top becomes 2 cube root of 2 squared, or 4. And then on the bottom, think about this. They're both cube roots, so you have to have like roots before you can multiply. 2 to the first times 2 to the second makes 2 to the third. And then, or you can think of it as 8, which is a perfect cube. The cube root of 8 comes out as 2, so it makes it perfect 2. And then in the numerator, just whatever it is, but we have radicals left for that. But notice here I have a 2 and a 2, so you are able to reduce that down a bit. And then you're left with the cube root of 2 squared. Let's go ahead and call that 4 for your final answer. All right, so reducing radicals, always when you divide, you need to rationalize it in some way to make the denominator perfect. A perfect square if it's a square root, a perfect cube if it's a cube root. Well, what if your denominator has more than one part to it? It's a binomial. I think that's supposed to be just square root of 2. Just it's a binomial or something different than just a one term like our other examples. There is a trick to rationalizing a binomial denominator that has a radical in it. We saw it a little earlier in the lesson. If you multiply it by its opposite sign, like the sum and difference, the same two terms, but one's a plus, one's a minus, that's called multiplying by the conjugate. You'll hear that word around in the algebra class. Multiplying by the conjugate always rationalizes your denominator. Again, whatever you do to the denominator, you have to do to the numerator, keeping the balance. So in the numerator, 1 times that will just make the 1 plus radical 2. And then in the denominator, we're going to FOIL that. First is 1. The outer is 1 radical 2. The inner is negative 1 radical 2. Those will cancel. And the last times last, the signs are different, is negative. Radical 2 times radical 2 is just regular 2 brought out. So what always happens when you multiply by the conjugate, the middle terms cancel, they're always opposites, and then the last terms are times themselves, so you wind up getting rid of the radical, so you get rational numbers. 1 minus 2, which we can work out is just negative 1. The numerator is 1 plus radical 2. You could leave it like that, or you could go ahead and say dividing by negative 1 would change the signs of the numerator, and that would, either one should be correct. All right, let's try that again. One more time, and you can pause the video if you like to practice on your own. I encourage you to do so, rationalizing this denominator. Let's do this. So we have a couple of radicals in this example, but because it's a binomial, there's 2 parts. You have to times it by its conjugate is the only way to get that rationalized. So timesing this by the same stuff, only the opposite sign will work. Whatever you times it by on the bottom, you have to times it by that on the top. And then we just have to clean that up. Alright, so in the numerator, this distributes. Because they're both square roots, we can times 3 times 5. I'm ignoring my phone, I'll call them back. Square root of 3 times square root of 3 is regular 3. So that's the numerator. In the denominator, we're using the FOIL method. The first, radical 5 times radical 5. Same, they're both radicals, square roots, same radicand, so it's like square root of 25 just comes out as a 5, or think of it as anytime a radical times itself just brings out the number that was underneath it. The outer will be minus radical 15, the inner will be plus radical 15, thus canceling out. And then the last times last, because the signs are different, is negative. Radical times itself just brings out that number 3. This top will not reduce. Those are not like terms. There's no perfect radical inside of 15 that I can bring out of that and reduce. In the bottom, I have these canceling. 5 minus 3 is 2. There's no other thing that I could possibly do to reduce that, so then that is your final answer.